12 on your
Presentation is on.
Good afternoon, everyone. My name is Poornaprajna. I'm a first year student. Today I'll be talking about something called attention. It is the core fundamental of almost all the new ML models that you can find in the market, such as GPT or Word. This is going to be like just a brief overview. It's like really complex, so I'm not going to go into like the huge details of it, but I'm trying to get my point across as much as possible. So, attention. It was introduced in 2017 in a groundbreaking paper called Attention is All You Need. In its basic structure, the core architecture of the attention mechanism is the transformer. The transformer is like, it's like, so up until then, we had stuff like RNNs, CNNs, and LSTMs, which stand for recurrent neural networks, convoluted neural networks, and long short memory. The thing is, they were good enough for like whatever we were trying to achieve, but they couldn't push the technology forward. So what they tried to do is they tried to introduce something called the transformer, which unlike RNNs and everything else, which goes word to word. So if there's a sentence which says the brown dog jumps over the lazy fox, it takes every single word. So it says the brown dog. The thing is, it works if it's a short sentence. If you're trying to get like lines of words or like sentences and like huge phrases and everything else, it fails terribly. So to beat that, they introduce attention and the transformer, which doesn't go word by word. It takes one word and it interlinks it with other using multiple heads instead of just like one mechanism going word. Each would take each word. So what it does better is one, which is the attention mechanism. The second, as I said, no recurrence, the previous mechanism, which is RNN. And more parallelizable because in RNNs, RNNs were like really bad at GPU utilization. So like for any machine learning or deep learning models, GPUs are essential. I think we all know. The thing is, RNNs were really bad at GPU utilization because when you use GPUs to run the whatever program or code or any model, it would use only one specific part of the code to run, to run through one word. So even if you had like 8 GPUs running 8 different RNNs, it will still not use the GPUs properly, efficiently. So this is just like a metric they use to see how forward machine learning is going. This is one of the metrics, which is BNEU or binomial evaluation unit score. Up until now, whatever we had is RNNs and LSTMs. They would usually do it for English to German and English to French, for the better of other languages. Whenever they did German and French, RNNs had a reported score of like something between 10 and 15, which had been groundbreaking for its time, but not really relevant as of now. So when attention, the transformers were introduced, it went from that core of 10 to 15 directly to 28.4 and 41.8, which is a huge leap. So this is just a metric they use to compare how much, how better it is. So this is the main mechanism of the transformer, which is the attention mechanism, which is what the paper is. So there's mainly two types of stacks in a transformer: the encoder and the decoder, both of which are made of 6 units. 6 threaded. So in the encoder, you have something called scale dot attention or self-attention. What it basically does is every single time you put a sentence to train it, it runs it as queries, keys, and values. The query is just like a question. It's saying, okay, what is this? It's just asking what it is. The key is like, it sets a value, not a value as such. It just says, okay, hey, this is my sentence, so this is my word, and this is where it is. And the value is just the meaning of the word. So like, if you have the in the sentence, the query is just like, what is this? And the key is, oh, this is like an article, and the value is just like, okay, it has this meaning, it just does this in the sentence. How it's better than an RNN is because RNNs don't have an understanding of the sentence. RNNs just do it word by word. Whereas here, it tries to understand. So because it has multiple different headers, it can do it much better. So what happens is you put an input, it runs the query, and then it assigns it a key and a value. And that is usually calculated using a scale dot product of the vectors which you got through the keys and values. Here, the thing is, it's based on the dimension of the vector. So it has, like, the formula is really complicated, but all you need to know is that it runs this program in which it uses the math, where it takes the square root of the dimension, or root dk, and it says, okay, this is how many inputs we can get and how many things we can get from the array of the vector body. So, and then we have something called the encoder, which has again like 6 stacks, like layers of understanding, 6 stacks of transformers to understand how it works. Where again we have multiple different heads. So you have self-attention and then you have multi-head self-attention. Self-attention works for one single stack, whereas multi-head is like the collection of all different heads. So now what we're basically doing is we are not okay. A very good example of this would be you guys read books. So when you read books, you just like you read one word by one word. You don't like just like, look at the page and go, I understood it, and you don't. That's what the attention mechanism does. It just looks at the page, it understands everything instantly. It assumes it starts from here, it associates it with something else, and because it's basically like trying to get 8 brains to read together one page at once. Whereas RNNs are like, it's just one, human, like one pair of eyes just looking at a book and saying, oh, this is what happens next. So multi-head attention is like really good at solving the problem of word by word linearity. So we have again, as I said, self-attention which does that. But why self-attention? Why not you might get a question, if we can just run multiple different RNNs parallelly, why not do that? Or LSTMs or any sort of model that existed before. Why is the attention factor? One was the hardware limitation, which I told you, it's terrible using GPUs. And one more is there is sequential linearity, which is in the RNNs, and then there is sequential operations, which the attention mechanism has, where it says every word is related to every other word, instead of just saying, oh, yours is related to the previous one. So if you had a short sentence, which is if the car is moving, it's fine, you can use an RNN. But if you have a long sentence, like a whole story, what is the guarantee that by the end of the book, the last word, the model recognizes that the last word is still somehow connected to the first one? And that's what attention does better, self-attention. And again, as I said, the path length. In RNNs, you start from the first word, you end at the last word. Correct? It's really, really long. You just keep going one word to another, one word to another. As I said, long sentences and crumbles. Whereas here, because of the multiple headers which you already have, and also the fact that it starts assigning some meaning between two words. So another thing is in RNNs, as I said, that if you write a sentence, the car is moving, it is fast. RNNs don't understand that it means car here. It just thinks, okay, the car is moving, it is fast, they are all different entities. So, it makes for a better, worse management, worse, if there's more data coming in, it really cannot handle it that way. Whereas this one, it understands, because of the multiple headers, one can understand it as okay, these are words. The other one can understand it as this is a verb, this is a noun. The other one will say, okay, this pronoun is related to the noun in the beginning. that it increases the length, because now it's not just a linear line, it's like a network. It's like this kind of this kind of, it's like a billboard that you're thinking of. This is just a dimension thing which I explained. So if you have 8 headers, like 8 multi-head components, it uses this formula where it says if you want to find the number of programs of number, it's a square. Can you guys see me? So yeah, it runs a program where if it's the number of cycles you can run, it's 64, which is 8 square. But then if you want to assign it to like each header, use the square root of the dimensions, which is like, depending on the usage, root 64 or root 8. This is just about what it does to make sure no matter how good a mechanism is, no matter how good a software is, you need to understand at the end of the day, it will not be perfect. It will have loose ends, it will have imperfections. And similar to anything that you do in engineering, you will try to introduce other fine-tuning mechanisms which will help it work better. For ML models, one of them is training. Like you need rigorous training. You can create an ML model right now. You can ask GPT, you can ask Gemini, you can go X for X. You can just create one right now. But then, if there is no training, it is as good as useless. So one thing is as I said, they use the BNE scores to find out how better it is than RNNs and LSTMs. And here they did it with English to German translations. And English to French translations, they use around 4.5 million sentences in English to German and 36 million sentences in English to French. As I said, 8 GPUs. The thing is, if you, as I mentioned earlier, if you use 8 RNNs on 8 GPUs, it still won't use it entirely. It will still be on word. Until it processes word number 1, it won't move on to word number 2. Whereas here, you already have the 8 GPUs and you have multi-head attention components. It runs it faster. So it can take the sentence, run it through all the 8 GPUs, and by the end of the line, when it produces the output, it's not just going to be, okay, I gave you the sentence, I know what it means. You can say, I know the sentence, I can translate it to this, I can do this as well. Because it was processed that many times and it was understood the relation between every single thing that you put as input. Optimizers, it's like a very big thing, so I don't go through much. But basically, you just need to understand that, they use something called the atom optimizer, so that the rate at which it learns and the rate at which how much training data it requires to reach a certain level of efficiency was all controlled by this. Not controlled, but it helped reach that level. And regularization, it was just hey, it did this thing. Okay, so there is in RNNs there's this thing called RNN with memory control and without memory control. With memory control is as I said, the read input. Whereas without memory control would be if I just came up to you with a flashlight and flash you, you would get light on your face and you would understand, oh, I got a flashlight, I'm going to get one again, and that's going to be related to the other one. But then what's the guarantee that you remember that the fifth flash is related to the first flash? There is no sense. Similarly, residual dropout does something similar to that in attention or transformers, where it says, okay, look, sometimes I just don't need this article or this one part of the sentence which doesn't do anything. So it can drop it for a while and it assigns it a very lower key value. It says you're not that important for me than the other person. And lane smoothing is something similar. It just says you have this meaning, you have this meaning, you can just go together. I don't need to store it separately. Okay, so before I go to this, I will say so I explained the encoder and decoder thing. There are different forms of attention within multi-head self-attention unit, and one of them is called encoder-decoder attention. So what happens is when you put an input in, it goes into the encoder, it processes it, and it says stuff. So what does it do? It runs a query and it sets a key value. And then you have the decoder. Okay, it's the decoder is like the reader. It just says, okay, the encoder is like the guy who recites the book, and the decoder is the guy who listens to it and translates it and writes it down. So when the results, outputs come out, the outputs are finally supposed to come out of the decoder, not the encoder. So when they come out, the decoder does something called reverse attention or reverse cross attention, where it takes the queries which were already run, which are like inbuilt in the decoder, and it takes the keys and values from the encoder. It doesn't run its own keys and values. So it's essentially saying, okay, what are you? But then every answer that I get is from you. I'm not creating the answers. If that makes sense. It's kind of complicated. Right? This is just something they wanted to do once the whole attention thing became popular, which most of it has become popular now. It's been used in research, it's been used in language parsing, or even audio. They're trying to now do it with audio and video files where it processes large, complex data, not just linear word files or math or whatever. Yeah, so that is what, in a brief, what attention does and is. So if you have any questions, you can ask. Was I audible? Was there a lot of fluctuation? Questions? Okay. So I did this, I presented this paper for my IO course as well. I attended an IO course which is made by Hemant. And the thing is, I did it on the last day. I presented this on the last day. I thought I'd be a little funny, and I put a little quote thinking it was really funny. I don't know why I did this. But yeah, that's pretty much it. Thank you. I'm assuming I got my point across.
Just end free. Just end. Yeah. On OBS if you end it, it should.